Hmm. So please type your attendance now in the chat box. Type your attendance. So in the chat box, write your roll number in full. Okay, let's start the class. So today we will continue our discussion on vector analysis, and we will talk about scalar function and the vector function and del operators, gradient, divergence, and curl. So I think everybody knows what a scalar function is. A scalar function is like, for example, a very common example here we can give is a temperature. Room temperature in your three-dimensional space can also be considered as a scalar function, because room temperature in your very own space, it varies with coordinate variables like x, y, and z value. So suppose you are sitting somewhere on your table and your body is generating heat. So just near your body surface, the temperature might be a little bit higher. But if you move a little bit away from your body surface, then the room temperature will slightly fall down, but to a very, very small fraction of degrees Celsius and all. So like that, it depends on where you are measuring the x, y, and z value. So those kind of scalar quantities which varies with space are called scalar function. There are actually the scalar quantities which are also constant, isn't it? Constant scalar quantities also you can have, like for example, mass of an object. If you take mass of a certain object, it's not a scalar function, but it's a scalar quantity, right? If mass of a certain object is a scalar quantity, it doesn't have any specific direction, but it's a scalar quantity, but it does not have any variation. Like if you move from one place to another place in your room, mass of that certain object will remain same, right? So then we have to see about derivative also. When we talk about derivative, I think in your mathematics class, you have already defined this derivative as a limit of this del f upon del x. So derivative, actually, when you take a derivative, it actually measures how quickly a function changes with a space variable or any let's say you take a certain function which is depending on a certain independent variable. So how quickly that function changes with that independent variable on which that function depends is what we know it as a derivative. It is a measure of that. So what we do in order to obtain a derivative, you have to mute yourself. It has unmuted, so that's disturbing. Yeah, I think everybody has muted. So if you look at this, for example, let's say you plot a function that is a function of x on the y-axis, and you plot the independent variable x on the z-axis like this. Now, if you take del f upon del x in this region, like for example, if you take something like this, suppose this is your, oops, suppose this the changes in x here is, let's say this is your del x, and corresponding to del x, what is the corresponding change in f value? The corresponding change in f value will be very small, del f, isn't it? So if you take the ratio del f upon del x here, this is very small. Now, derivative at a certain point is simply when you consider the limit that your increment in x, your increment in the independent variable is very, very small. When you consider, when you take the fact that when the increment in the independent variable is very, very small, that is del x tending to 0, then del f upon del x at such condition when del x tends to 0 is called your derivative df upon dx at a certain point in space. Okay, so as you see here, even for a significantly large change in del x value, the change in f is very, very small. So the derivative is very small. That means the function f changes very slowly with x, or the change in x hardly affects the functional value. So as I said here, as I have stated here, it is a measure of how quickly the function changes with that variable. All right. But if you consider this region here, now you take the same interval length, let's say the same length here, del x. If you consider the same del x, the same increment in x, the same increment in x will result in what? Significantly large change in functional value. So in this region, del f upon del x is quite large, right? This is quite large. So at any point in this region, if you want to consider the derivative at that point, then you have to consider del x, the increment tending to 0. So the limit del x tending to 0, this will give you your del f upon del x. And here you will find that in this region, this ratio is quite large. That means this function f can quickly change with any change in x value. So derivative, it measures how quickly a function changes with a space variable. Okay, so I just want to point out that probably you already know it from the perspective of the physical meaning of this derivative. Okay, you know this mathematical form, but you have to see the actual uh, meaning of derivative of a function. Now we have a del operator. So it's a vector operator in the sense that this del operator, when it operates on scalar quantities, it becomes a vector, right? It does not have any physical meaning. So if you ask me what is the physical meaning of a del operator as it is, it does not have anything, right? But only that it is certain mathematical operator, but having a vector quantities like I cap, j cap, k cap, they are the unit vectors along the three-dimensional Cartesian coordinates x, y, and z axis. Right. So only when it acts on certain physical, like scalar and vector function, it has a physical meaning. We will look into that. So scalar functions we have already discussed. Vector functions are vector quantities which changes with space variables. Like for example, if you consider a force or a magnetic field, also a magnetic field in a space changes from one place to another place, isn't it? So a magnetic field, if you have a non-uniform magnetic field and non-uniform electric field, so they are vector quantities, but non-uniform means depending on where you are, like according to the space coordinates, those quantities like magnetic field, vector, and electric field, and all they changes, right? So those kind of functions are, in general, we can consider them as a vector function. And gradient. So I can see that only few of you, oh yeah, how many of you have typed your attendance? Please don't forget to type your attendance in the chat box. Type your roll number in full and type it correctly. So if you have entered your attendance once, please do not repeat it. So the first attendance I can see in my chat screen is 2101 BS277. BS277. If anybody typed before BS277, please retype it again, because if you type your attendance before I joined the session, that will not be recorded in my chat record, so I cannot record your attendance. If anyone type your attendance before BS277, type your attendance, enter your attendance again. Otherwise, no need. Once you entered your attendance there, it remains there in my chat record. So everything is recorded with me. No need to worry about that. Okay. So del operator operating on a scalar function is called the gradient. As you can see, like for example, if we consider phi to be a scalar function, which is a function of x, y, and z, then del operator, when it operates on such scalar function, is called the gradient of scalar function phi. So this is how it is. So when this vector quantity or vector operates on this scalar quantity, this scalar function will be differentiated with x, will be differentiated with y, and also z. And divergence is when this del operator operates on a vector function, and in between this vector operator and the vector function, if there is a dot product, then that is called a divergence. Okay, so now let's look into it. So here we consider a scalar function which is a function of x, y, and z. All right, so we have already talked about derivative. Derivative is a measure of how quickly a function changes with that particular variable. And also we know that, like, if phi is a function of x only, then differentiation of phi with respect to x, is called normal derivative. So in normal derivative, we simply use the notation d here. Differentiation of phi with respect to x is called normal derivative if phi is a function of single variable x only. Oops. Now, in this case, this will be limit del x tending to 0, del phi, change in phi with respect to change in x. This is how we take a derivative, right? Now, when we have function phi, which is depending on more than one variable, that is x, y, and z, then in order to find the change in phi, any infinitesimally change in phi, we need to consider how quickly this function changes with x, how quickly this function changes with y, how quickly this function changes with z, right? So when the function is depending only on one variable, whenever we talk about change in phi, it has to be change in phi with respect to change in x only, right? But if we have a function which is depending on more than one variable, when we are going to consider change in that function, change in function can occur with respect to changes in x. Change in function phi can occur with respect to changes in y, and similarly change in phi can also occur with respect to changes in z, right? So because of that, we have to consider how quickly this function, or how quickly this function changes with each and every variables on which this function depends, right? So such such measurement, a measure of how this phi changes with x, is called partial derivative of phi with respect to x. All right, a measure of phi, how phi quickly changes with y, is called partial derivative of y with respect to y, partial derivative of phi with respect to z. So I hope you understand what I mean by what we mean by partial derivative here, because phi now has a function, phi now has a dependencies on more than one variable, and uh, uh, depending on the functional form, phi may quickly change with x, however phi may not change with y, or however the changes in phi with respect to z might be very slow also. So it all depends on the functional form. So the functional form will determine what these partial derivatives will give, right? So, and here, what is dx? Dx, as we already talked about, dx is small increment or small changes in x, small increment in x, small increment in x, small increment in x. And similarly, dy is small increment in y, and dz is small increment in z. So in order to change this function phi, you see that, like, let's say you have a certain three-dimensional space, something like this. If you have a certain phi here, if you have certain phi here, if you have to change phi value, if you have to change phi value, phi is a scalar function. That means phi depends on x, y, and z. This is x, this is y, exists, this is z. Phi is a scalar function which depends on x, y, and z. So let's say you have a certain phi value. At a certain point, phi value is fixed. Phi value is fixed at this certain point. In order to change this phi, you need to move a little bit away from this fixed point. Let's say we go to another point here, right? So if you move to another point here, what you have to consider is how much is the change in x and how much is the change in y, and let's say how much is the change in z. So when you when you change the space variables by a small amount, del x, del y, and del z, then you can move phi from one location to another location. Let me repeat. Let's say we have a certain function phi, which is a function of space variables like x, y, and z. So if you fix the value of x, y, and z, then phi value will be fixed in one particular space. And but if you move to another location here, let's say this location is the coordinates of this location is x plus dx, y plus dy, z plus dz. So here previously the coordinates was x, y, z, but if you move to another location, we can consider that location as x plus dx, y plus dy plus z plus dz. So what is dx? From this, if you move along the x-axis, the small changes along the small movement along the small increment along x-axis is called dx. Small increment along the y-axis is called dy. Small changes along the z-axis is called dz. So when you change the space variables, only then you can move from one location in space to another location in space. So when you move the space, when you changes the space variables, then only you will find change in phi. So change in phi will be associated with change in space variables, right? So dx is how much you are moving along the x coordinates, dy is how much you are moving along the y coordinate, and dz also is how much you are moving along the z coordinate. So as you change the space variables like that, you can see that the change, there's a change in phi, right? So and as you move along x-axis, how quickly the function will change with respect to changes in x is given by this. As you move along the y-axis, how quickly the function changes when y is given by this, and similarly, this how quickly this function changes with z is given by this, right? So this theorem on partial derivatives, this is in mathematics, so this is nothing you need to memorize or anything complicated at all. So if you have to find any incremental change in this function phi, then this is given by this d phi is equal to del phi upon this. And uh, if you employ vector calculations, like for example, let me go back here. Let's say your vector is a1i plus a2j plus a3k. Let's say your another vector is b1i plus b2j plus b3k. So if you take a dot product, a dot with b vector, you take a dot product means a1i plus a2j. So this is something very basic, but still then I want to start with a very basic, because all of you may not be on the same platform, I mean on the same level of understanding. So let me start with very basic and then I can move quickly later on. So if you take a dot product, I dot I is 1. That means A1, B1 plus I dot J is 0, I dot K is 0, right? So similarly, if you consider that A2, B2, A3, B3. So if you have a product like this, A1, B1 plus A2, B2 plus A3, B3, that can be written as A dot B vector. All right. So similar to that, this scalar quantity can be written as grad phi dot dx here. I hope you understand this. So considering the analogy with the dot product I just explained. Now, this quantity, as we already defined, this is called the gradient of a scalar function phi, gradient of a scalar function phi, and dxi increment along the x-axis, increment along the y-axis, increment along the z-axis. And you know that like position vector, we call this quantity as a position vector. I don't know. Yeah, this is called position vector. I need the space actually. Position vector. Position vector in a Cartesian three-dimensional space, R vector is xi plus yj plus zk. This is called position vector. Okay. Now, changes in position vector, dr vector is like written like this: dxi plus dyj plus dzk vector. Okay. Changes or small incremental changes in the position vector is given like this. How you are moving in a three-dimensional space, right? Like for example, let me draw it here. Let's say this is x-axis, this is y-axis, this is z-axis, and let's say this is the origin, and from here, if you take this point, the position of this point can be this distance defined as a distance from the origin, right? So the vector defining this position is called the position vector, r vector. Now if you move to another point here, this increment or small change in r vector is called dr vector. Okay, so the new vector here, the new position vector here will be, if you consider vector addition law, this will be r vector plus dr vector. I hope you know this. Okay, so dr vector is simply changes in the position vector. So the original position vector is r vector. The new position vector will be r vector plus dr vector. All right. So when you are moving in this three-dimensional space, the changes in the position is measured by dr, and that vector quantity is called this dr vector. So you can see that any changes in phi can be expressed as gradient of phi dot product with r vector. All right. Now let's see. Let us try to understand the physical meaning of gradient. So any change in phi is a dot product between grad phi and dr. So if you take a dot product like this, a dot b is actually magnitude of a, magnitude of b, and cos theta. Theta is the angle between a and b vector. And similar to that, if you take a grad phi dot dr vector, this will be magnitude of grad phi dot with dr vector. Sorry, not dot. Dot product is magnitude of grad phi, magnitude of dr vector cos theta. Okay, so this is exactly, so from this relation, if you take a dot product between these two, this is what you're going to get. Now theta is the angle between this vector, grad phi vector, and dr vector. Now you see that if phi is 0, that means the angle between grad phi and dr vector is 0, then cos theta is 1. That is the maximum value for cos theta. So here you can see that for a fixed value of dr, change in the scalar function d phi will be maximum if theta equals 0. So let's say this is your dr vector and this is your d grad phi vector. If you consider dr vector to be along the same direction as your grad phi direction, that is when your theta here is 0, then you will have maximum change in the scalar function. Okay, so let's say you have a region of phase x, y, and z here. You have a certain scalar function phi here, and you can move from this one space to another space like this dr. You can choose your dr along this direction. You can move to another point here, or from here you can even move up here. By moving up here means your dr is vector is like this, or you can move down from this position to this position, so your dr vector will be something like this. So you can move your phi from one, like your phi, your scalar function, from one location in space to another location in space in any direction. You can choose your dr vector, your movement in any direction from one space to in this three-dimensional space. So if you choose your dr vector such that your dr vector is equal to your the vector direction of this gradient of scalar function, then you will find that phi will have maximum change, or it will have a maximum effect on phi values, right? So then what we can see here is that grad phi is a measure of the direction. It defines the direction of maximum change in the scalar function in space. Okay, grad phi defines the direction of maximum change in the scalar function in space. Just a minute, I got a message. So we have to add 2101 BS091 Azon Sangi. I hope she is here in the WhatsApp group. Zone Sangi at NM 2101 BS091.
Yes, sir.
Okay, so you have to be included in our attendance sheet. That's the message I just received from our HOD. So think about it. This del operator, as we talk about, it was simply a mathematical operator, vector operator, which operates on scalar quantity. Del operator, as it is, it does not have any physical meaning, but when it operates on scalar function like phi, it will define the direction in space along which we can have maximum changes in phi, So like that. Okay, now I think if we continue our lecture, I think the thing will be more clear to you. And now let's talk about this vector function. So vector function means like if you have a certain fixed function, you can have a fixed function like this. For example, 3i plus 2j plus 1k. For example, if you consider this is a constant vector. How do I say that this is a constant vector? This is a vector quantity, of course, but it has a fixed magnitude. This would be a fixed magnitude 3 square plus 2 square plus 1 square. You can find out the magnitude, right? Or if you move from, suppose you consider a three-dimensional space like this, x, y, z. This quantity will not change with x, y, z values. If you put this vector here, it will have certain magnitude of this length. If you put here also, it will have the same magnitude, because the magnitude of this vector does not have any x, y, z dependence, right? But if you consider a vector quantity, for example, something like this, vector to be 3x I 2 x y cube z j plus uh, x y z square k cap, for example. If you consider this vector quantity, it has dependence. The magnitude depends on x, y, and z. So that means if you move from one space, like let's say here, if the magnitude of the vector is this much, but if you move to another space, the magnitude and direction might also change. So the magnitude and direction could also change from according to these x, y, and z values, right? Those kind of vector quantities are called vector function. It happens in non-uniform electric field and non-uniform magnetic field also, right? Now, divergence is when this del operator operates on this vector quantity. And when it operates on vector quantity means when there is a dot product between this vector operator, del operator, and this vector function. So if you have a dot product here, I dot I is 1. So that means del A upon del X, del A2 upon del Y, del A3 upon del Z. This is called divergence of the vector field A. So I hope you understand what is a constant vector and vector field. Okay, vector field means the vector quantity which depends on, as you can see, this vector quantity depends on x, y, and z. Any vector quantity that depends on x, y, and z are called vector field. Any vector quantity that depends on x, y, and z. Now, let's look at this. For example, if you consider this vector, a vector is xi plus yj. See, as you can see, vector A depends on x, y, and z. Here you see that vector A depends on x and y, actually x and y. It depends on x and y. That means if you move in this space coordinates, that is from one location or one values of like let's say one values of x and y values to another values of x and y, then this quantity will change. Then that means this vector quantity, it changes from one space to another space, one location in space to another location in space. That means this is a vector field. Now let us try to draw this vector field xi plus yj. Let me consider a two-dimensional space, something like this. This is x-axis, this is y-axis. Let's say we consider 0, 0 point. At 0, 0 point, x is 0, y is 0, your vector will be 0i, 0j, 0, no vector. Now let us consider 0, 1. At 0, 1, if you look at this, x value is 0, y value is 1. So 0i plus 1j. Okay, so your a vector is 1j. So what is 0, 1? Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Please mute 3, 4, 5, 6, 7. The point 0, 1, this is 0, x-axis is 0, y-axis is 1, means this is the point. We consider the point under consideration here, right? So at this point, the vector A will have unit magnitude and it will be pointing along the y-axis, because j cap is unit vector along the y-axis. K cap is I cap is unit vector along the x-axis. So if you consider here, your vector will be point like this. Now if you consider 1, 0 point, what is 1, 0 point? This is your 1, 0 here. X value is 1, y value is 0. So your a vector will be 1i plus 0j. So this will be I cap 1 into I. So that means here, if your vector will be, your vector field will be having this direction, having unit magnitude. Now if you consider the point 1 1. If you consider 1 1, this is x-axis is 1, y-axis is 1, so the point y1 is 1 1 is this point. So out here your a vector will be 1i 1j. So this will be your vector 1i 1j. What is the magnitude of this? Magnitude of this will be square root of 1 square plus 1. So it will have a magnitude of square root of 2. Square root of 2 is what? 1.12 something, isn't it? Square root of 2. And give me the I don't have the exact value. So square root of 2, if you take it, 1.1 something will be there. Now 1.14 or like that. Now here, out here, the vector 1i, the vector 1i is something like this. The vector 1j is something like this. If you consider addition of these two vectors 1i and 1j, according to law of vector addition law, rectangular law, like for example, you have one vector here and you have another vector here. If you add these two vectors, the resultant of these two vectors is when you construct a rectangle or something like this, then this is the resultant vector, isn't it? This is the resultant vector. So exactly, if you have 1i 1j vector, the resultant vector will be pointing something like this. So the magnitude here, the magnitude of this vector will be 1.12 or something like that. Okay. Now, if you consider another point, for example, 2 1. If you consider another point 2 1 here, a vector will be 2i plus 1j. So what is the magnitude of this vector? The magnitude of this vector is square root of 2 plus 1 square, that is 4 plus 5. So square root of 5 is what? 2 point something. 2 times 2 is 4, so 2.4 or something like that. Square root of 5 is, I don't know the exact number, you can calculate it also. Square root of 5 is having a magnitude of 2.4 something. All right, so what is this vector now? 2 1. X value is 2 1 2. Y value is 1 2 1 1. So 2 1 point, the space is the point value, the space coordinate is this. This is your 2 1. Okay. Out here, what you have is 2i vector. So 1 2 2i vector. What do you have? 1j vector, 1j vector. So what is the resultant at this point? The resultant vector at this point here is something like this. Okay. Now, if you consider 1 2 vector, making it a little bit more elaborate, 1 minus 2, for example, 1 minus 2, minus 1 minus 2. So this will be minus I minus 2j. What is minus I minus 2j? The magnitude of this vector is again square root of 5. This will be 2.4 something. 2.4 something again. Now minus 1 minus 2j. So if you minus 1 is this point, minus 1 is this point, minus 2j is this point, minus 2 is this point. So the space coordinate out here is this point. At this point, the vector, you have a minus 2j here and minus 1 here. So the resultant vector at this point will be something like this. Okay. So all in all, what you're going to have here is something like this. Closer to the origin, you have a smaller vector like this. But if you move away from the origin, the vector magnitude becomes larger, something like this. If you construct all the vectors in this two-dimensional space, what you will have is something like this. Again, if you move further away, the vector magnitude will become bigger and bigger, something like this. Okay, so as you can see here, you will find a vector field which is pointing or diverging away from the origin. If you construct this vector in this x and y space, you will find that it will represent a vector field which is pointing away or diverging away from the origin. Vector field in the sense that towards the origin, when the space coordinates x and y values are small, the vector magnitudes are small. But if you move away a little bit further away, when the x and y coordinates values are increasing, the vector magnitude also will become larger like this. So you have a diverging or a vector field pointing or traveling away from the origin, right? So this is what this mathematical form xi cap plus yj will represent as a vector in this space. Now, when you take a dot product with this del divergence of A, you will find that here I dot I is 1. That means del x upon del x is this, del y upon del y. So del x upon del x is 1, del y upon del y is 1. So 1 plus 1 is 2. So you have a divergence of the vector field A as to certain finite value. Okay. Now let us look at this vector, another vector. This. As you can see, this is a fixed vector. It has a like a certain fixed magnitude. So, and this vector is having unit magnitude, and it is pointing along the y-axis. The vector direction is defined by j cap here. The vector is pointing along the y-axis. So you have vectors of fixed magnitude pointing along the y-axis. So if you plot in this xy space, this is what you're going to have. So the magnitude is 1. Everywhere the magnitude is 1. In this space, the magnitude is 1 in everywhere in this space. And the vectors are all pointing towards along the y-axis, j cap direction. Now, if you take a divergent in this vector, you will find that divergent of A is 0. Del 1 upon, here you see that, not this, del 1 upon y actually. I dot j is 0, j dot j is 1, so del 1 upon del y is 0, k dot j is 0. So what we can see here is that this vector, what is represented, the vector which is represented by this expression is like this. If you take any region of space here, the amount of vector field, the amount of vector entering this space is equal to the amount of vector leaving this. So let's say 1, 2, 3, 4, 5, 6, 7 vectors are entering this space. 1, 2, 3, 4, 5, 6, 7. 7 of them are leaving. So there is no net outflow of this vector. No net outflow of this vector. The amount of, or no net inflow, no net inflow, as well as no net outflow in this case. Amount of vector entering the region of space is equal to amount of vector leaving the region of space. You can consider any region of space here. You can consider the space here also. Out here, 3 vectors are entering, 3 vectors are leaving. That means no net inflow, no net outflow. That means the vector is not diverging from any region of space. But on the other hand, if you look at this vector here, you consider certain space, for example. In this certain space like this, there is no inflow of vector. Only vectors are flowing away from this, isn't it? The only vectors are flowing away from this. So that means this vector is diverging. It gives what is called an outflow of a vector field. So when there is a net outflow of a vector field, then you will find that the divergence is certain finite quantity. But in this particular example, when there is no net outflow or no net inflow, the divergent is 0. Okay. Now let us look into what is called, I'm about to conclude, physical meaning of divergence. In any region of space, divergence of a vector field measures the net outflow or inflow. Forgot to mention net outflow or inflow of the vector field in that region of space under consideration. All right. Like for example, if you consider electric field due to a certain point charge here, if it is a positive charge, the electric field will be diverging, or the electric field will be flowing out from that point. If it is a negative charge, then there will be a net inflow of the electric field. Okay. The divergence will be finite. Here in this case, the divergence will be minus. Here in this case, the divergence will be positive. There is a net outflow, there is a net inflow here. All right. But if you consider a magnetic field, you know that magnetic poles always exist in pair. Now, the lines of force originates from North Pole and terminates at South Pole. So for every magnetic lines of force originating from the North Pole, there will be a magnetic lines of force terminating at the South Pole, right? So if you consider the region of space bounded by this surface here, you can count how many magnetic vector field are leaving this: 1, 2, 3, 4, 5, 6, 7, 8, and correspondingly 8 of them will enter this region of space. And similarly, if you consider this region of space, you will find that 1, 2, 3 magnetic field vector lines are entering, and 3 of them are leaving magnetic field vector line. uh, three of them are entering and 3 of them are leaving this region of space again. That means there is no net inflow or no net outflow in this region of space also. So because of that, the divergence of magnetic field is always 0. Yeah, divergence of magnetic field is always 0. Magnetic fields are non-divergent field because of the existence of magnetic poles always in pair. There is no monopole. It always exists in South Pole and North Pole. Even if you cut a bar magnet, you will still have a North Pole and South Pole, right? So the magnetic lines of force originates from North Pole and terminates at South Pole, and therefore you will find that consider any region of space, there will not be any net outflow or net inflow of a vector field, a magnetic field. And then thus you find that divergence of magnetic field is always 0. So divergence, when we talk about a vector field divergence, it is a measure of the net outflow or inflow of a vector field in any region of space under consideration. Yeah, so I think I should stop here. I was thinking of discussing Carl also, but I think we should stop. So like going I think probably very slow. Probably in next class we can do a little bit faster. I will take one extra class this week, probably in the evening during night time. Okay, so I will announce that. I'll stop here. Thank you, everyone.